Hi guys, today I'd like to show you guys a cool nucleophilic addition reaction example. Sorry for the blurry GIFs, but I have these here so that it covers up the work and the final answer so that I can go through each step one by one. So as we see here, we have a molecule. We know that it is a cyclohexane attached to an alcohol and a ketone. And if we look at our reagents, we have CH3Li, which is an organolithium, which is a form of an organometallic. And if we know and think back to our previous chapters, we know that organometallics are responsible for turning aldehydes and ketones into alcohols. Same with Grignard reagents, but currently I'm only talking about an organometallic. The second step is an acid workup, and this is very common in creating alcohols because you'll see in the work down below that we'll have an issue once we remove one of the hydrogens from the OH. Okay, so I'll get rid of this real quick now. So it's a lot, but we'll go one step at a time. So right here, we know that we have our organolithium. And essentially, our organolithium is an organic compound attached to a metal atom. And basically, we know that it is CH3 and Li. Since we know that the Li is a spectator ion, it won't really matter in the abstraction of hydrogen. So we can write the CH3, which is basically a methyl ion, up here. And if we look at this, what can this nucleophile take away from what we have right here? Well, we know that this negative will try to abstract this hydrogen, and that basically allows the bond between H and O to go on itself on the oxygen as well. That causes our oxygen to essentially have 3 lone pairs, making the formal charge -1. And a side product is going to be CH4. That's because as the methyl ion was taking away the hydrogen, it gained a hydrogen. So that means it filled its octet, and now the formal charge will be neutral. And then if we look down here, like I mentioned, the oxygen will have a -1 formal charge due to the extra lone pair set. And in this case, this is where the acid comes in. Since this isn't really stable and very reactive in nature, nature wants it to be more stable and less reactive. And that's why we have an acid workup in these problems. The acid in the solution will allow one of the lone pairs of the oxygen to grab one of the hydrogens from the hydronium ion, and that will basically complete the octet by forming a bond between O and H, and this will be turned into H2O as one of the hydrogens got abstracted. So if we look up here and take away this blur, this is our final product. So essentially a bond had formed between the H and the O due to the acid workup, and nothing else had really changed in the molecule because it's not really what the reagents would have done. And if you look, it's actually really funny because there is no net reaction. And I think this is really cool because usually in organic chemistry, when we see different reagents, different synthesis, different types of reactions, we always get something drastically different, or maybe not drastic, but something different. And the fact that we have the same original reactant, I think is really cool.